morning. My name is Cory, and I'm going to talk to you about serverless security. From the conversation I had yesterday during the happy hour, I got the sense or the feeling that not everybody understands exactly what serverless is. I'm going to spend maybe 2 minutes just explaining the concepts, and then we'll jump to serverless security. But before that, a little bit about me. My name is Cory. I'm the CTO and co-founder of a small startup called PureSec, based out of Tel Aviv, Israel, that invented the serverless security space back in 2016. I've been involved in application security since the end of the 90s. Was fortunate enough to work on the research of some industry-leading products like IBM AppScan and Akamai Kona Cloud Security. And those of you who are old enough to remember Sanctum App Shield, which was the world's first web application firewall. I actually had a patent for that. I'm also the author of 20 patents in the field of application security, mostly around static analysis, dynamic analysis, interactive application security testing, and also published a few, I guess, popular or known security articles, research articles, one of which pretty much gives my age, the Apache remote code execution back in 2002. So that's a little bit about me. I'm also the guitarist of the Israeli popular art rock band called Pitts. If you're into alternative, noisy music, you can go ahead and download our albums. So I have about 35 minutes today, and so I'm going to try to concentrate on what's really important. We'll quickly cover what is serverless security, what am I actually talking about when I'm saying serverless security. We'll focus on a few risks and pitfalls. Dave actually mentioned some of them very relevant. And then we'll see a live demo of how we hack a real-world serverless application. That's going to be a good experience to understand the problems as well as the benefits of serverless. And then I created a short list of action items for you guys. So I promised I'll explain what serverless is, but very quickly, serverless is the latest abstraction in the cloud model. If you look historically at how people deployed applications, starting with bare metal and then VMs, containers, and now serverless, the main things to notice is that people are losing interest in being able to manage infrastructure, in deploying things, taking care of security patches, and so forth. And on the other side, want to concentrate on their core business logic and what they know to do best. So this is where serverless takes us. That's the latest abstraction or the latest step in this evolution. Specifically, the benefits from serverless, first of all, there are no servers for you to manage. And yes, there are servers somewhere underneath everything that you're using, but you don't really care about them. Continuous scaling, so you don't have to worry about capacity planning and scaling. If you have an API, it can scale from one user at a time to thousands of concurrent executions. You're being billed by the millisecond or 100 millisecond intervals in most cases. And of course, from a security perspective, you have a lot less to worry about. And we'll get to that in the next slide. Just to give you a quick explanation of how serverless security has been approached, looking at the first 3 years of serverless, if we're looking at AWS Lambda launch in 2014 as the epoch here. Then in the beginning, people said, it's not my servers, I don't have to care, I just have to care about the, how my applications handle input. And today, people understand that that's not really what's going on. There's still a lot for you to worry about, a lot of you to things that you have to take care of, and we'll get back to that. The shared model of responsibility, we can't have a cloud security talk without mentioning that. In the case of serverless, the cloud provider is responsible for almost everything, from the physical security of the locations, the guards, the locks, the server racks, and so forth, all the way up to the container that's running the serverless runtime where your code runs. So that's a lot of tasks, security tasks that you don't have to worry about. On the other hand, you still have to worry about the security of your own application. And that's your responsibility, and that's not going to change anytime soon. Nobody's going to take the responsibility for the code that you are writing. And in serverless, that pretty much means the functions themselves, the functions that you write, your code, the logic, as well as the identities, the access management, the configuration of the cloud resources that your application interacts with, and obviously the data. I published this white paper a few months ago, trying to take the list of PCI security requirements with some additional other requirements. The list is in a small font for a reason. It's not really relevant, but there's a huge list of tasks that when you are running your own bare metal or infrastructure as a service, VMs in the cloud, you're responsible for. From patching the OS and hardening the OS and authenticating users and network segmentation and everything. That's the blue part. That's you, the application owner, that is responsible for. So pretty much 90% or 92% is still your responsibility. When you move to serverless, things get much better, as I mentioned earlier. And the majority of tasks related to the underlying infrastructure is now under the supervision or the responsibility of the cloud provider. And you're left with 48% in this case, but you see it's pretty much half and half. So from that aspect, serverless gives you a great starting point from a security perspective. I'll explain how serverless works very quickly, just so I can explain some of the attack surfaces. So a developer deploys code through their code repository, pushes it out to the cloud. That's called a function. A function is tied to event sources. Could be an S3 bucket that changes, a database table that changes, an HTTP request, a WebSocket request that comes in, telemetry data coming from an IoT device. There are plenty, I believe 47 different event sources that can trigger AWS Lambda as an example. And that will trigger your code that will run, do its job. Usually the code is not an island. It's not isolated. It will communicate with cloud resources like buckets and databases and so forth. And if everything works well, it will generate some output. How can an attacker actually approach or reach your business logic in the cloud, given that it's deployed in your account? So we see a few paths for that happening. The first one is through the event data itself. So when the event triggers your function, it brings with it data. I'll give you a very simplistic example. An HTTP request as an event trigger will bring in the data from the HTTP request, parameters, cookies, URLs, headers, etc. That's very easy to understand. When the event trigger is something more cloud native, like a database table that changes, or an S3 bucket that is being changed or manipulated, then the event includes data from whatever triggers the function, and each event source has its own event format and its own encoding schemes, and so there are enough attacker or user-controlled or attacker-controlled fields to manipulate. So that's one way to manipulate your business logic. Think about a function that gets invoked by a change in an S3 bucket. Then the name of the file, for example, could be an attacker-controlled, could be the input vector in this case. Unauthorized deployment, and there was Dave mentioned, credentials, cloud credentials. There's a wide range of attacks that an attacker can pull off in order to gain the ability to deploy functions to the cloud, starting with cross-site scripting to a developer's machine, or phishing attack, getting the credentials, and deploying the function directly, not through your regular CI/CD pipeline. Another way through the code, which is not by hijacking credentials, is by poisoning third-party dependencies, and this is something that we're starting to see more often. There's a bunch of NPM packages that have been poisoned in the past few months, some of them to run, I believe, crypto mining code. And this is not specific for serverless. However, in a serverless environment where you don't control the underlying infrastructure, it's harder for you to know that these things are happening. So in a normal environment, you can monitor the third-party library, see what's it doing during runtime. In a serverless environment, we'll see how you can handle that later, but it's a bit harder. And last but not least, as I mentioned, when these functions run, they interact with cloud services. If those cloud services are publicly available or accessible to the attacker, he or she can manipulate the function. Think about a function that interacts with an S3 bucket during execution. If I can manipulate the contents of the bucket during execution, the function will, will be manipulated to do some other things. And what can an attacker actually achieve from this? That's pretty much normal or standard to what we're seeing in application security, compromising data, abusing the business logic, bypassing authentication, leaking secrets, even denial of service is a thing an issue that you need to think about because these functions, when they run, they do have concurrency limits, either on the function or on the account. And if I can get the function, and you'll see how we can do that in a second, if I can get the function to overwork, and I can instantiate enough concurrent execution, I can choke the account and deny other users from using your applications. I'm not going to go over the list of top risks for serverless security. I've done that in this article, this guide that we published together with the CSA a couple of months ago, called the top 12 most critical risks for serverless applications. These are the ones that are pretty much aligned with the OWASP top 10, with a few that are very unique to serverless. And even those that are aligned with the OWASP top 10 have their own twist or their own nuances that are serverless related. But we will see a few of those live in a second. There's a need for serverless native protection. And if you look at traditional security solutions, you see that in order to deploy them, you need to have access to the underlying infrastructure. So think about a web application firewall or a runtime application self-protection, or even network security solutions that you use to protect the application layer. You need to deploy them somewhere, either on the network or on the host. That's how they work. In serverless, by definition, you don't own the network, you don't own the infrastructure, and so you're out of luck. You're out of luck, and you're not in liberty to deploy these solutions, which means that these traditional security solutions are becoming unsuitable for serverless architectures. And to put that into a diagram, if today you build an application, let's say it's a web app. You install an EPP endpoint protection on the host itself to monitor the behavior, an IPS on the network, web security gateway to inspect outbound traffic from your application, a next-gen firewall, obviously, to inspect inbound traffic, and then you add a web application firewall to inspect layer 7 traffic, and all of that sits on the infrastructure today, either on the network or on the server. When you go serverless, you break up the application into functions. You deploy the functions to the cloud, another word for the internet, and without these infrastructure-based protections, and users obviously can access your functions and invoke them, but so can attackers. And so without any cloud native or serverless native protection, your security is basically reduced to how good you wrote the code and how well your configurations were done, and we all know that the human factor plays a big role here. So we'll talk about a few of the risks, and I'm glad that Dave mentioned this. Identity and access management is going to be the first one. So let's see what the challenge with least privilege IAM roles means for serverless functions. In this case, you see a sample of a code snippet where a developer is using DynamoDB, a NoSQL database that AWS provides, and is inserting data into the table using the put item API call. If you are adhering to the least privileged concept, and you should be, you should only give or grant the function permissions to put items into that table. And that's something that actually didn't exist in monolithic non-cloud applications. If you had a SQL server, your application would usually be able to do both read and write operations on the table. AWS IAM model is very, very powerful and gives you the ability to define that your function should only be allowed to put items into a very specific table. So the model is very powerful, however, it's hard to get it right. Usually what developers will do, and we can discuss the reasons for that, is grant a wildcard permission to the function. The reason developers do that could be laziness, lack of awareness to the problems that this is causing, and we'll see that in a second, or trying to future-proof the code. If we know that this function will be used for other things in the future and we don't want to suffer the IAM permission error, we can just give it all of the permissions on Dynamo. Quick quiz, anyone can actually name and spell the correct IAM permission that you need to use in order to put items into Dynamo? Come on. At least one? No? Put item, however, it's spelled with camel casing. Makes perfect sense. And so most developers don't know that. They need to go into the documentation and find the relevant permission. It's not very easy to find that, by the way. And so that's why this is happening. Now, what happens when you grant a wildcard permission on Dynamo? That's very bad. So all of these permissions that you see here, all of these actions are now allowed for the function. So the function can delete the table, can delete an item, and we'll actually see that in a second. So, by the way, we ran, I think last year, we ran a scan of 1,000 GitHub serverless projects, open source, and we found that, I believe, 21% of them had critical problems just like this one. So this is the most common issue, and as you will see in a second, actually, if you do handle it properly, IAM permissions together with the microservice-oriented architecture that serverless helps you to build can be terrific for security purposes. It can act like bulkheads in a ship, where if somebody finds a vulnerability, a very severe vulnerability in one function, you can pretty much limit them and contain the damage to one location, and we'll see that in a second. And the second arrived. Back in August, this is a friend of mine, Caleb Sima. How many of you know him? Oh, terrific. So Caleb came out with this challenge, trying to sort of like a bounty hunt. He created an extremely vulnerable serverless function that basically allows you to run code through a website, and offered a $1,000 bounty to whoever manages to do some serious damage to his cloud account. This is me when I saw the challenge, and of course I said, you know, this is a terrific opportunity to get some PR out of this, so let's try. So the nice thing about this function is that it's basically a remote code execution given to you on a silver platter, right? This is like the holy grail for attackers, getting remote code execution, and you'll see how frustrating this actually was in the serverless case. So the first thing I did was to run the env command to get the environment variables. And I saw a few variables here, 3 of which, you only see one of them, are related to the session that the function has with the AWS environment. So when the function starts running, it assumes the role that we talked about a second ago, and it gets a session for that role. And that session is denoted by 3 parameters, the session tokens, and then a couple other more, the access key and the secret key. So what I've done is I copied them, and I actually use this Mac to set these environment variables locally. Why would I want to do that? Because then I can impersonate the Lambda function and use its user to run whatever I want from my local machine instead of using Caleb's very ugly web interface. So I've done that. I've exported the variables, and then in order to check whether I'm now really running under the Lambda's permissions, I ran the API getCallerIdentity, and lo and behold, I was running as the Lambda basic execution role, which was terrific. This is me when I discovered that I am running now as Lambda. So the first thing I did was to see if I can list the other functions in Caleb's account. And so I ran list functions, but then I got an access denied exception. So that was the first thing that didn't quite work. Obviously, Caleb somehow hardened his IAM role. And so I tried a few other things. I tried to get the source code of the function. That didn't work as well. I tried to list buckets on the account. That didn't work as well. And then we were pretty much doomed. And I was sitting for about 3 days saying, OK, he was smart enough to lock down his IAM role. I'm not going to get anywhere with this. And so then I said, you know what? Usually, when there's a website, there is an S3 bucket that stores the static files, right? And usually that bucket will have the name of the domain. So I tried that, and I got an empty response, or just an empty line out of that. And so I was thinking, wait, is an empty line a problem, or is the bucket really there? And so I tried something completely different, like a made-up name, and I got a 404 out of that. And so I said, OK, there is a bucket. That's interesting. Let's see if I can list the contents of Caleb's bucket. And so I tried list object on the bucket, and indeed I got a list of all the files in that bucket. So that was very cool. Sort of like a directory listing of the old world web servers. Next, I say it will be really cool if I can have write permissions on that bucket. Maybe I can write a file, so showing Caleb that I managed to store some files there. And so I don't know what went through my head when I was doing this. I decided maybe I can delete something that will prove that I have write permissions, right? Well, that's an overkill. And so, yeah. And so the next thing was a phone call from Caleb that the site was down. So I deleted the index file. Nobody could reach the file. On one hand, I was winning and nobody else can access the site. On the other hand, I came out like an idiot. And so Caleb was actually at Black Hat back then. It was August, and so the site was down for 5 days, which was terrific for me for tweeting purposes and PR. So how do you get IAM permissions right? And in this case, by the way, the S3 bucket wasn't publicly open. You couldn't do that without impersonating the Lambda role. It was the Lambda role that had the excessive permissions. First of all, you need to adopt a role per function model, where each function has its own role. And think about, I think there's another principle called the principle of single responsibility or something like that. Your function should be doing something very specific and should have very specific permissions for that. And so a role per function will help you get that. Think twice before you use the asterisk or the wildcard, obviously. If you can, and if you're using AWS and you're using SAM to deploy your serverless applications as a framework, it's a framework for deploying serverless applications, you can use SAM managed policies. This is how you would define that. And if you really want to screw things up, you can, using SAM managed policies, give full access to the database, but you don't want to do that. The right way to do that is to use a custom role per function, as I mentioned, and then basically say that this role is only allowed to put an item into that specific table. That's the right way to do things. Getting it right is easy on one function. It becomes a bit of a problem when you try to scale. And so PureSec, my company, actually offers a free open source code scanning tool that you can scan your Lambda function code, and then it will auto-generate an IAM role that is least privileged based on the static analysis of your code. So it basically extracts which APIs you're calling, on what resources, and generates a relevant role. Let's talk about app REDOS very quickly. How many of you know Cory Quinn? Same people. So Cory is a very funny guy, very cynical, and has a newsletter that talks about AWS AWS bills. That's what he does, helps people with their AWS bills and make it more efficient and reduce costs. And his newsletter is very cynical and sarcastic, which is always fun to read. And he approached me a few months ago and said, you know, I have this newsletter. The registration is done through a Lambda application. Maybe you can hack it if you will. I will blog about PureSec, etc. He did mention that it's not really doing anything important, so the potential for damage here is very low. And so I started looking. He actually exposed the source code for this. Started looking, and we saw that he was using, or Cory was using SendGrid, a very popular library for doing emails. And SendGrid creates, takes the user's email and creates an object out of that. And that's using actually the Python's native email package. And that package supports these long email formats where you have the actual name and then the email. And usually I say, you know, when there's a parser, I'm pretty sure there's going to be some fun involved here. If you like reading RFCs, you can go through the RFC and see what this is all about. But the thing that, you know, looking at the code, I figured out that that library will work slowly if presented with very specific input, like this, obviously legitimate email. So I tried this, obviously in an email format, and that took a few more milliseconds to run. But then if you do 100 kilobyte long email address, the library will stall for about, I believe, 2 to 5 seconds. And, well, that's good enough. Now, this is not really a serverless attack, right? I'm just doing a RDoS attack here. However, if you post this 1,000 times concurrently, and you only need to do it once, and you can use you know, a small laptop, you'll basically take up all of the resources in the account, and you'll hit the account concurrency limit, and nobody can use the application or that account for that matter. And that actually worked. And a few seconds later, we got an internal server error. And funny enough, Lambda didn't recuperate from that. It took about 2 minutes. So the site was down for about 2 minutes. As promised, Cory wrote something, generated a spike on the PureSec website, and everything was terrific. I'm going to skip the last example. It's pretty similar. You can read about it in our blog because I want to get to the demo. And in the demo, I've actually created an HR application that 100% serverless running on AWS Lambda. It's very cool in the way it works. A candidate will send an email with his or her CV as a PDF file, and that PDF file will get handled by the Amazon Simple Email Service, and we'll pass it through an SNS pub sub message to trigger my Lambda function. The purpose of Lambda in life is to extract the PDF contents, turn them into plain text, analyze the contents of, or the qualifications of the candidate, store the results in the database, and then send an email back, and also expose a web interface for the HR team to invite people to interviews or store their, you know, archive their stuff. And so let's interact with this application. Give me a moment. Now, the fun thing about this is that you don't need to build an interface. It's an email. So I'll send an email. Let's say I'm a job candidate, and my name is John Smith. If you want to see this, this should be better. And then my CV is attached, and I'll attach the CV. Now, the CV is a regular computer science CV. There's no malware in here hiding in the PDF, although that would be cool. Let's just send this. And here's the cool part. Remember, I'm not managing any servers right now. The email is going through, simple email service, SNS, triggers my Lambda function, does textual qualification analysis, store the results in a SQL database, NoSQL database, sends me a receipt back, and also exposes a front-end interface for the HR team. I think, never mind. I should have it somewhere, but trust me, it works. And so we got the receipt email back. Now, let's say, for the purpose of the story, that we didn't get accepted to the job, and we want to get our revenge. And our way of doing that is going to try to leak the database of sensitive candidate information back to the cloud. So how do we do that? If this was a web-based interface, that would be pretty easy. I would spin up like something like a SQL map or some fuzzing tool, start fuzzing with the different form parameters, right? However, I'm using email, and I'm not going to try to attack Amazon's email, you know, hosted email service, managed email service. I need something else. If we look at, you know, the amount of entry points we have to the application, it's not much. We have the file itself and the contents of the file. So the file name and the contents, we can assume that something inside the application is using the file name, maybe to copy it from one location to another, or to extract the contents of the PDF. And so what we'll do is we'll copy the file, and we'll modify it a little bit. So I'll do John, semicolon, and then let's do sleep 5000 hash. I'm using a trick here called a time-based probe. Assuming that something is using the file name inside a shell interpreter environment, the semicolon sleep is going to cause that interpreter to sleep for 5,000 seconds. In most systems, that will cause a timeout. In Lambda, that will obviously cause a timeout because the default is 5 minutes. And that will be our signal that the system is indeed vulnerable. So I'm not expecting the developer to send me any stack traces back over email, right? That's not very plausible. So just waiting for it. It took about 10 seconds earlier to get a response back, maybe 15 seconds. So if that's not going to happen, I'll know that my file name is a good way to inject OS commands into the environment, and it is. So the next thing we want to do is we want to turn this black box engagement into a white box engagement. And how do we do that? We want to get the source code of the function back. And that's probably in serverless going to be the first thing that attackers will try to do. So how do we do that? So I'm actually storing this thing on Pastebin, where it's available to anyone on the internet, and also to Lambda. And all this Python code does is extract the name of the function, of the file name, and then it opens it up and reads the source code and sends it back as an email. Now, at this point, it's sitting in Pastebin. I need somehow to get it into Lambda and to execute. How do I do that? So very similar to what we've done with the sleep command, slightly more sophisticated. Instead of semicolon sleep, I'm using semicolon, some ugly things, curl to fetch data from Pastebin, and then pipe it into a Python child process, which is always there. How do I do that? And obviously .pdf at the end, because it's a legitimate file name. And then we'll send that. And in about 10 or 15 seconds, we'll get 2 emails back. The first one is the receipt email. The second one is the source code of the function. Now, if you look in CloudTrail, which Dave mentioned earlier, or CloudWatch, you won't see any traces to the fact that we just stole the source code. The reason is that we didn't violate any IAM policy. It's okay for the function to access its own source code and obviously to access the internet. And so we got the 2 emails back. Here's the source code, and we'll quickly go over it. I have a minute, which should be enough. So the developer is defining some table name, taking it from an environment variable. Not the best security, but better than hard coding. We do see it's a DynamoDB client. And then this is where the function is defined. They're getting the input, getting the file, extracting the file name. Good security practice to whitelist the file name, checking that it ends with a .pdf, and then using that to actually run a very common CLI tool called PDF to text, which eventually does what it says, translate PDF into plain text. However, embedding untrusted user input in that command. So when we type semicolon sleep, we basically split that command into 2, the original developer command and our own second command. And then the developer is using dynamo.putItem, and we'll see how we can abuse that right now to get the data out from the application. So how do we do that? Again, I'm storing my malicious payload on Pastebin. Just a second. There it is. My payload is very simple. It creates its own Dynamo client and then runs dynamo.scan, which is the API to scan the entire table, fetch the data. I don't even know the table name. I'm reusing the environment variable, which is very convenient, and then dumping the data back into the response email. Again, I need to somehow run this on Lambda, so we'll do this. And very similar trick to what we've done earlier, curl, fetch the data from Pastebin, and pipe it into the Python 3 child process, and we'll run this. Here's the trick. The developer should have given the function only the put item permissions, but as you've seen, it's very popular to give it a bit more. One of those permissions was the ability to run dynamo.scan. And that is what the problem here was. In about 10 seconds, we'll get the entire dump of the database table back. Keep in mind that it took us 3 emails from probing to full exfiltration of the database, very under the radar. Doesn't require like thousands of HTTP requests using SQL map to exfiltrate the data. And if somebody asks you, is it possible to inject and exfiltrate data from a NoSQL cloud native database, here's the proof. Obviously, it required 2 things from us. One is the ability to inject OS commands, and the second one was the bad permissions. And here you see the real problem. If the developer or would have given the function only the put item permissions, the only thing we would be able to do is insert items into the table. But the developer gave it a bit more than what was needed. So, quick take action. Right, so I prepared this short list. This is a good Twitter photo op moment. Yeah, go ahead. Don't forget to tag me. The first one is the CSA top 12 serverless security risks that I mentioned. It covers AWS, Google Cloud, IBM Cloud Functions, and Azure Functions topics as well. The AWS Lambda Security Best Practices book that I published a few months ago. OS Serverless Goat is a terrific example. It's a live application with a single click of a button. You can deploy it on AWS through the app repo and learn how to attack and defend your serverless applications. You can then show off your skills to your teammates. I mentioned the, actually I missed that, but Function Shield is a free library that developers can use to tame open source dependencies on serverless environments. And have a look at the serverless security platforms that are available. There are a few options other than PureSec as well. That's it. Thank you.